the next chapter in the book, but kind of a continuation still about what's going on in the nucleus. So we looked at 25.1.3 and then 26.1, and now we're jumping to 26.3. 26.2 actually is an interesting section. It's a new section. The old book didn't have it, so that's why it seems like there's a jump in it. So the new book talks a lot about radioactive decay, a lot, which is usually our part of the chemistry course. So it's in section 26.2. We don't have the time for one more lesson. This is like looking at exactly where it is, so I'm not going to go through that. But if you want to, if you're intrigued by it, radioactive decay, because I know you guys have a lot of questions about specific uranium and stuff, we're going to talk about fission and fusion and those processes. But more specifics about radioactive decay, such as analyzed and stuff, is all in section 26.2. So if you want to see that, we can talk about, like, for example, I kind of read into it a little bit, because you're asking a lot of good questions yesterday about it. And the way uranium works is that it's giving off radiation, that's radioactive decay. And when it gives off radiation, that's energy. And what Einstein theorized is that energy and mass are really the same thing. So it actually is losing some of its mass. So remember I was saying, I don't think it's like losing its mass, or it's not going, it is losing some, it's not really disappearing completely, but some of its mass is physically being converted into radiation. And that process involves neutrinos and some other smaller particles that we haven't discussed yet. Like beta waves and certain waves that are radiation waves. And each of them have a certain amount of energy. Based on how much energy that is, you can convert and see how much mass was lost using E equals mc squared. So that's that standard format everybody's seen in Einstein, right? So everybody thinks it's the most famous one. And it is. Because there's a lot more than just that. That's where that also comes from, is used. We're going to talk about that in general today, but if you want to see a little bit more of the math, I would say, take a look at 26.2. It's not hard math at all. It's just different stuff that we haven't talked about. So first, any sort of nuclear reaction involves a change in the nucleus. That's really what's important here. Because if it doesn't involve a change in the nucleus, it's just the electrons, right? The valence electrons can move from one atom to another, making one of those atoms an ion, or making them charged, whether they're positive or negative charges. So, for example, one of the examples I wrote down here, and this is our example here, is this nitrogen atom is bombarded by helium, okay? And this is an alpha particle, by the way. Helium is an alpha particle. It's one of the radiation particles. So just helium itself. So it's bombarded by that. It results into an unstable nucleus, which is fluorine. That's this right here. And then since fluorine is unstable in that state, fluorine then splits off. And you end up getting oxygen out and hydrogen. And you can look at a little mass balance, right? 2 and 7 is 9, 9 is 8 and 1, so we can see that we have a balance there. We have 4 and 14 is 18, 17 and 1 is 18. So we're not changing the amount of mass that exists in this process, but we're kind of restructuring it in a sense. Okay, we're restructuring it in a sense.
I thought I was asking about the radius, like from F to O plus H, that did happen to uranium, just because we can stay.
Yeah, the next one we'll go into uranium. We're going to go into that example, but it does. Uranium is bombarded by, I think it's a neutron actually. And the neutron causes a chain reaction, which splits the barium and krypton. And then that continues down the line. I'll show a diagram, so you can see it. But it is the same concept. It is the same concept. And we're now going to go more specific. This is a general nuclear reaction where there's a change in the nucleus. But the change in the nucleus can be because it splits or because two nuclei come together. So when these first two nuclei merge, they become this, that's fusion. And when this nucleus splits, they become these two, that's fission. So this was a fusion and fission reaction kind of together here. But we're going to specifically take a look into fission first. So fission is when the nucleus splits. When it splits. This only happens for heavy nuclei. Heavy nuclei, like regularly split. So generally speaking, atomic number greater than 58. Doesn't have to be a number you can memorize, but just generally understanding that the heavier the nucleus, the more unstable it is. That's what we talked about yesterday, because that strong force, which is the nuclear force, only works at very small distances. So if the nucleus keeps getting bigger and bigger, strong force is not as strong when it gets bigger. So those nuclei that are rather large become more and more unstable as they gain more and more mass.
So in this case, we're talking about atomic nuclei greater than 58, approximately. The nucleus itself, when it splits, releases energy. And again, so I'll jot that first part down. When it releases energy, that system itself loses some mass in the form of energy. Okay, so again, it releases energy. Well, the only way that can happen is if the mass goes down. You can calculate how much mass is actually decreased or lost in the reaction if you use this formula and you know the amount of energy. I'm pretty sure in these categories, energy is measured in electron volts. If you recall from the last section, we talked about EV, electron volts. It's another unit for joules. I don't think we use joules here to measure energy because joules are such a large quantity. So when we think about things, by the way, we talked about how there are 4,186 joules in a calorie, but then there's a lot more, 10 to the 19 electron volts in a joule. So calories, what we burn, are like a big energy unit. Then you have joules, which are the smaller energy unit. Then you have electron volts, which are like the microscopic energy unit. So when we talk about energy on this scale, this small, we're using this electron volts here. Now, we're not going to do the math, but just to give you an idea of what we've done. It's not hard, obviously. They measure this electron volts. The mass, believe it or not, can actually work using electron volts. And then C is in meters per second. Speed of light. So when this occurs, when fission actually happens, and the nucleus splits, you get resulting energy coming off of it that we're talking about. Now, you can get photons. So these are like your byproducts. You can get photons that come off. Photons are light traveling. Light traveling. Did I tell you guys that joke ever? A photon walks into a hotel. The guy says, "Let me get your luggage." He says, "Oh, it's okay, I'm traveling light." That's a good one, right? So it could be photons, which is light energy. It's light energy. And then it could also be protons or neutrons. Now, the one that's kind of important is actually neutrons. The way a lot of fission occurs is by saying to the nucleus, "Hey, take on some extra weight. We're going to throw a bunch of weight at you in the form of neutrons." And those neutrons make that the nucleus heavier and larger and becoming unstable. Well, when the byproduct becomes another neutron, that neutron goes to the next atom. It says, "I'm going to make you unstable." And then your byproduct is a neutron, it makes him unstable. His byproduct is a neutron, it makes you unstable. So the neutron going as a result, as a byproduct, causes a chain reaction.
So each byproduct
Causes the next reaction. And it's chain, it's a domino effect.
So kind of like how the atom bomb works?
Yeah, I mean, it's a fission bond. An atom bomb is a fission bond. That's a fancy name for it, but yeah, splitting the atom, that's the whole concept of it, yeah? Take a look at the equation for this. So, actually, I'll put the equation on the next line. Take a look, So let's take a look first at what's happening with the chain reaction. So U-235 undergoes fission. It releases around 2.5 neutrons when this happens. Those 2.5 neutrons, it's showing 3, okay, showing 3. Those 2.5 neutrons hit the next atom of uranium, causing it to split. Now, in the first case, it's barium and krypton that come as a byproduct, and then 3 neutrons. But then, when you have iron and krypton, you have rubidium and cesium, and you have palladium, I think, and bromine. Palladium and bromine? I think it's palladium. But what I'm trying to get at is that uranium splits into other stuff too. And as a result of what do you see always as a byproduct? Neutrons. Those neutrons hit the next uranium each time, and causing those to then split. So this is the chain reaction I was discussing a minute ago. So this is fission. Now, if you can control fission and keep it at what's called its critical state, you gain energy from that. Nuclear fission is actually user energy. There are fission reactors. This is the energy that we can use. Fusion we cannot use yet. Fusion, it takes more energy to put in than we get out. It's not worth it. Fission we do use. It's where you have these cores, they're nuclear cores of uranium, and they're underwater to keep them cold, but are also creates creates gas from that water, which that gas then turns a steam engine, which creates energy. So your nuclear power plants have chain reactions occurring at all times, but they're controlled. If they weren't controlled, you would have what's called a meltdown. The nuclear meltdown. Chernobyl, you want to give an example of that? That's why people are so afraid of having nuclear energy. It's because of the fact that there's a possibility for an uncontrolled chain reaction. But that's the same thing as a forest fire. A forest fire is exactly that, right? Just on a bigger scale. On a bigger scale. It affects people radiation-wise. So it's a lot more dangerous, obviously. You definitely don't have a lot of people living in the area, for sure. Absolutely. There is a radiation signature. But radiation, thankfully, decreases, I think, as the square of the distance from it. So if you get far enough out, it's not like it's going to affect you. But yes, it's not fully controlled. The people work in these buildings, and they get tested for radiation all the time. All the time. So if you're, for example, a guy that works on replacing nuclear cores, you can't be near them for more than like a half an hour a day. And then that's it for the day because it's such a high radiation. When you get tested on the way out, your body, you physically, they scan how much radiation you've gained from that day. It's very interesting, I know, it's scary, it's a scary job. If you look at your textbook, there's some really good pictures of this. Of a person physically replacing, and they put what are called little beads of uranium, the pellets, to replace what's being used up in the core. That's where I recognize the mass must be increasing. Yeah.
Isn't there still radiation in Chernobyl?
There's still a radiation signature from that as a result, and it definitely did affect the body, outstanding area.
Yeah,
But that was because it was a meltdown, because it was uncontrolled. These are controlled reactions. Now, if you know how much radiation you're producing, you know the amount of energy, and you know the limitation, and you keep the system running at that sort of a reaction, it's fine. But Chernobyl was a meltdown where it actually, literally, the process underwent. You had a failure in the system, pretty much. There was an electrical failure and a failsafe. And the temperature and pressure scales weren't reading properly, so bad. So when they thought everything was okay, it wasn't.
I think that's crazy. Like, I think like the animals there are really messed up.
They talked about there being like animals with like 3 or 4 legs in the front instead of 2, like there being actual mutation. I mean, that's what X-Men is, but on a different scale, right?
Yeah.
It's mutation. The body mutates over time, it changes, and that radiation level causes quick mutation, not like eons, and, where you're like looking at like hardware as you adapt over time. This is like a quick change. Joe, you know?
I was just gonna say, I read something, I don't know if this is true, but that there are bugs there that are immune to radiation now because they've lived there for so long, and they're trying to research that to see if that can help cure cancer.
Makes sense. I mean, they talk about how cockroaches specifically are going to survive nuclear fires. Like the one creature that will always exist because it doesn't affect them. So are there bugs there that now, as a result of this, are immune to it? Probably. It's a good chance. Yeah. I was going to write down the reaction for this. You don't have to memorize it, so you can just look. You don't have to actually write it down. But it's a neutron again, right? A neutron with only mass, no proton to it, bombarding uranium, and it's U-235.
What do you mean by only mass? No.
A neutron doesn't have a net charge. It's positive and negative, right? So if we talk about a proton is a 1 down here and a 1 up here, right? Because a proton is pretty much hydrogen. A proton by itself is hydrogen. So seeing the 1 here with the mass.
So it doesn't have
It doesn't have a charge to it. If it was an electron, if it was a proton, it would have a positive or negative charge.
Neutron is
So
just, okay.
the neutron is neutral. Yeah, neutral.
It's like what's even not nucleus and nuclear proton, right? And neutron is what's on the nucleus of this
Protons. Yeah, that's right. That's what's inside. There's plus minus signs, you saw. And this results. Oops. This results in. I'm going to do the first reaction here, okay? So the first one was barium and krypton. So, or kryptonite, I guess it is. This one, no. What is it? Is it kryptonite, or am I just thinking of Superman right now? What is the actual? Is it?
There's Krypton.
Krypton is the planet in Superman. Kryptonite is the stuff on the table. It's Krypton or kryptonite.
It's Krypton, I think.
Okay. You just telling me this, or you just?
No.
Okay.
It's just
You can pull my leg right now. So barium and krypton. But the byproduct again are around 3 neutrons. Really 2.5. But to balance it, we put a 3.
It becomes just like there's BARBCS, they're just random.
So these are 2 elements that come as a result, but then they show that uranium is split into 2 other elements, which is bromine and this one. Or again, these 2, or rubidium and cesium. So, because again, the mass is still not going to change.
So that the first time you can change it to any of the
Correct.
three, right?
Correct. This is just an example shot. Yes.
This is just like
I mean, this really is just this portion of the collision, right here. So if I just zoom in on this region right here, isn't it this? I could zoom in on this to start it, or this. So it could be any of those byproducts, not just those.
Is it randomly just?
I don't know, actually, Rodrigo. It's a good question. Like, meaning the result of it, which one will it be? I don't know. But again, the key is this, guys. The key is this. The result of the reaction isn't what matters. It's the energy that is released when the reaction occurs. When you split a nucleus, you're breaking intermolecular bonds, which have potential energy, really. It's internal energy. There is so much energy in those bonds that when you break them, these resulting nuclei and these neutrons are not what are important. It's the energy as a result. And usually that energy comes in the form of radiation. That radiation, as a result, heats up some sort of a fluid like water, which then causes that to boil off or boil into becoming steam or a gas, which turns a turbine. That turbine turns a magnet. That magnet rotating generates electrical energy in a current, a solenoid. The DC motor that we're going to build next class is exactly this. It spins it, which creates electrical energy that gets stored in a capacitor or a battery. That battery then provides energy. This whole process undergoing, it's the energy that comes out of this that matters in the form of some electromagnetic radiation. Let me give you some fun facts, okay? Fun facts. You know what TNT is? TNT? Dynamite? Yep, dynamite. What was dynamite used for originally? For mining, mainly, yeah. For excavating in general, you could use the word excavating. So if you wanted to build a tunnel through a mountain or something, you had controlled explosions with dynamite. So here's a fun fact for you. Ready? 1 kilogram of uranium holds as much energy as 20,000 tons of dynamite. A ton is 2,000 pounds. A ton is a car. 20,000 cars in mass of dynamite. Dynamite used to be like the thing, right? The most explosive thing is 1 kilogram of uranium energy. That's how much energy you get from nuclear fission reactions. Just to give you an idea of this, right? It's incredible to think about it. There are nuclear power plants in northern New York. Where are they? Anybody know? Upstate New York, I'm pretty sure there are nuclear power plants that use fission. I don't know. Okay, I thought maybe some of you come from up that area. What's that?
Know where I've been.
Not where you've been?
Yeah, know where I've been.
None where you. Nowhere you've been. Got it. I thought you said like you know where I've been, as if you've been affected. I'm like, are you like dissing yourself right now? I don't understand this.
There's one in Buckingham. I don't know how to say that.
Buckingham?
I guess.
There's apparently a total of 5.
In the U.S.?
No, for New York.
Or New York? That sounds reasonable.
Yeah, are you making like a top 10 YouTube channel?
Say again?
Have you ever thought of making like a top 10 YouTube channel? You seem like the type that would be able to do it. Like,
You have like the voice, yes.
Yeah, you have like the voice, like the top 10 facts of the day or something.
Oh, top 10.
Post one of those videos. Yeah, I can see you doing that.
Science related?
Yeah, like so. Yeah, I can.
You're hysterical. All right.
Top 10 physics of-
I don't know. So let's go on to fusion now. Let's go on to fusion. So that was mode 1, right? Fission. If you can't remember which is which, think of the word fuse. Not fuse like a fuse box. But when two things fuse together, they become one. I gave the example already, right, of Dragon Ball Z. Did I reference that? Here? Did I not? Dragon Ball Z.
When?
Who knows Dragon Ball Z? You know Dragon
I
Ball
was
Z, right?
thinking about that too. but
Fusion.
you
Goku
do
and
it,
Vegeta.
yeah.
They come together. You do their a little dance, right? Or War. They did you remember the years? You remember that
I
one?
do.
Majin Buu Saga? That was a good one. I've seen all 290 episodes of it.
I've seen the Dragon Ball.
Did you see Dragon Ball also?
Yeah,
So, when I
that's
was a
on
young
GT.
kid,
It was really bad.
yeah, GT was not good. Like, they kind of like made it never happened, right?
Yeah.
Yeah, when I saw Dragon Ball, I was a really young kid. Probably like 8 years old when it came out, I think. But Dragon Ball Z was like the show to watch. We used to watch Dragon Ball Z before we went to church on Sunday morning. My mom would get so upset because it was all like fighting and killing. Like, you're going to church, what are you doing? Like that on the show. Let's watch it. There were 4 of us, so we don't watch it. But anyway, great show. And they fused in the show. So in the show, they fused together to be one person. That's why I think of fusion. Anyhow, so a nuclear reaction where 2 or more nuclei combine to become one. So this is generally for light nuclei, not heavy ones.
Can I tell you one thing more?
Yeah, go. Yeah, I'm sure.
I was listening to a YouTube video about a guy that makes like theories and stuff, and he was like explaining how the
Kamehameha
is
works?
like real, but they like warm their key like warms up like the air so much that it becomes plastic, and they just do that.
I've seen a couple on who has more energy, Goku or Superman, or have you seen those? Or like who would win in a fight between Goku and like Super. It's always Goku versus some superhero. Because like Wolverine can't die, right? That's why they do like Wolverine, you know, X-Men. Even when he's decapitated, technically one dies still. So like who would win that fight, right? So there's a thing on Goku versus Superman, and they say that Goku has more energy. When he becomes Super Saiyan 3 or higher, he has more energy than Superman. And it's kind of cool, but yeah.
There's like this channel that does like death battles, but Superman beat Goku in that one.
Did he?
Yeah, he killed him.
Okay, I didn't know that. I did not know that. Why didn't Goku just use kryptonite?
Oh,
Goku should have just got some kryptonite, fused it with his Kamehameha wave, and shot it at him. I mean, that would have been the way to go.
On the video, they like Goku has the kryptonite, and like he sees Superman like get weak and destroys him.
He's like on honorable.
Because he is on. That's true. Goku's all about honor. That's right. Remember with Vegeta when he lets him fight again, where he doesn't kill him in the beginning of the first one? That was one of the best series in the beginning of Vegeta. I love that show.
The terrible movie Dragon Ball Evolution. That like.
There were like 10. Well, yes, with the real life one.
Yeah.
Oh, it was terrible.
Bad.
Absolutely terrible.
Really bad.
With the girl who played Chun-Li.
Oh my god.
Yeah,
I think that was
she
the
played
worst
Chun-Li
movie.
in the real life version of Street Fighter also.
Yeah, I think that was the worst movie I've ever seen. Like Goku was like this angsty teen that always
Yeah.
wanted to fight. Yeah.
No, but they had movies. They had like 10 movies that were actually animated ones, like the Tree of Might. Remember those? Those movies were actually pretty good.
Oh, yeah.
The Legend of Brody is another one of them. Brody, which was, do you remember he was Goku's like stepbrother who was off in another galaxy that came to like take over?
Oh, yeah.
Or Rashek was another one. Yeah. What a show. What a show. If you haven't seen it, highly recommended. A lot of physics involved, a lot of energy. All right, let's see what else. Okay, so fusion releases more energy than fission. Fusion, the energy released is greater than fission here. Per unit mass, I'm saying, per unit mass. The byproducts this time are not, remember last time it was neutrons, protons, and what was the last thing I said in that one? It was neutron, proton, and something else. And photons, thank you. Light energy, duh, joke. This one releases gamma radiation. It releases positrons and neutrinos. Oh, I'm sorry. Oh my gosh, there was nobody there because they the thing. Yes, Mom's came in late, I know that. Ella was not there, I think she's in the exam. Kate McConnell was not there, she's in the exam. Andre's here. Peter was here for sure. Ann was here for sure. Chris Bell was here. Will was here. Alexa was here. I'm missing one person. Is that it? No, Christian Content, but was he in the exam as well?
He's in the exam.
Sorry about that. Thank you, Samantha. Oh, sorry. It's tough. I have all you guys in class. I always forget. I'm always like,
What was that about?
mentor didn't.
Oh.
So gamma radiation, positrons, and neutrinos. Somebody, do me a favor, I always confuse the two. Look those up, positrons and neutrinos. What are they exactly? I think one of them's like one of them's just mass and then charge or something. Take a look at what those are. Maybe we can people who's research and read out what they are. This is not my area of expertise. I've told you guys that. But I try to read up on it as much as possible. What do you got? Okay, so a positron, right? Positron will have much less mass than a proton, but will have a proton's charge for each. It says it's the same mass as an electron is what a positron is, but it has a positive charge. So think of it like a proton, but not massive like a proton. And then the other one was a neutrino. You read it?
Particle with mass close to 0 and 3 carbon, lower mass, not 0 or 3. The relative reaction will normally matter. There's 2 carbons. Actually,
So neutrino. Searching your scent for that video, maybe airplane actually, because I'm trying to think back on that. That was a while ago. The fourth thing we'll jot down here. The fourth thing is what's happening here is that it's generating a ton of heat. It's called a thermonuclear fusion reaction. Okay, the first hydrogen bomb was a thermonuclear fusion bomb, really. Essentially, it's uncontrolled. Now, here's the problem with fusion right now. Fusion, although it creates, and we'll go to the next slide for this, although it creates a lot of energy, right, there's a desire to capture it because it creates a lot more energy than fission does, it's not able to be controlled, A, well, and B, to control it takes more energy than you get out of it. So, imagine, right? Exactly, it's a waste of energy. If it takes me 20,000 joules of electrical energy to produce something else that only gives me 15,000 joules, I probably wouldn't do that, right? Because I'd be losing 5,000 joules in the process. So to harness nuclear fusion reactions, you have high temperatures, so high that they become plasma. But the plasma can't touch the outside of the container because it would melt through the container. So it has to supercharge magnetic plates on the side to keep the plasma together in the center. But the energy to charge those magnetic plates is more than the energy gained from the plasma itself. So it doesn't make sense to do it. They're getting close to a break-even point. What would that mean, break-even point? What do you mean by that?
Like middle energy is lost or gained.
Good. What you put in is what you get out. Now, we don't want that either. Well, yeah, we really don't want that either. Because it would be taking fossil fuel energy to create that energy, so it's not really clean energy in the end. But if we can use, say, a kilogram of coal to create a city's worth of energy, then it makes sense, right? That's the whole premise behind what we want. Now, give me one sec. The material that's widely used for fusion is actually hydrogen. And hydrogen is far the most abundant thing on Earth. Water is hydrogen and oxygen. So the whole idea is that if you can get a controlled hydrogen reactor, you can have hydrogen that powers things. So hydrogen cars are actually being made now, but they're not very stable. Upon collision, hydrogen gas would explode, it's very volatile. So there's issues with it right now still. The concept would be to use hydrogen energy in thermonuclear reactions to create energy itself because of the abundance in the galaxy. And the other parts are. Anybody read Ender's Game? I recommend it. Did you? You read the first one?
Yeah.
There's 4 to the meat, there's 12 books in the whole
Yeah, I
thing.
know, I read the
But there are
first
4 in the small series.
Yeah, and then there was a movie about it too.
Yeah, the movie just came out.
Yeah.
Or 2 or 3 years
Yeah,
ago.
a while ago.
So there are 4 of them in the first series. If you haven't gotten to them, you like the first 2, the last 2 are so much better.
Really?
It talks about traveling with the speed of light and how it changes time and time dilation. They talk about landing on planets to refuel with hydrogen because of the water that's abundant on other planets. and then using the hydrogen with the fusion reactor to give them energy, which is exactly this.
Yeah, I know.
It's a lot of like real modern physics here. But yeah, keep reading if you enjoy it.
Seems like your type of book.
It's awesome. It's awesome. I've read the first 4. I never got to the next 8 because they're 3 miniseries, 4, and it's a different perspective of a different character in the next one. So I didn't really get into it. Right now I'm in an even better series. Well, not even better. I shouldn't say that because that was so good. And I'm in a series now called Mistborn. Another one. We're controlling metal. I think I talked about it in this class, the other class. They control metal, kind of like Magneto style, but using metal and the energy in metal to give the person like superpowers, but using the energy stored in the metallic bonds, which is kind of what's happening with fission, not fusion, but fission. That's exactly right. So the sun, I was about to talk about the sun here. Yep, the sun is pretty much a constant hydrogen bomb. It's a thermonuclear fusion reaction that's occurring on the surface of the sun because of the abundance of helium. Okay, the helium that's reacting, the byproduct here, and it's a lot of hydrogen on the sun itself. I'm trying to think of the surface of it, but the sun is mainly, remember helios we talked about? The atomic spectra of the light coming from the sun, helios. So helium reacting with helium, causing a byproduct of a different form of helium, one of the isotopes, along with hydrogen. This is one of the examples of a fusion reaction. Again, though, the sun is a great example, and the sun is constantly losing mass. Constantly. That's why the sun has an estimated life. We know when the sun's going to stop burning. And since the sun takes 8 seconds for its energy, or 8 seconds or minutes? I forget which one it is. Is it minutes? Thank you. For the sun, it takes 8 minutes. When the sun burns out one day from far away from now, it's going to be like, there's going to be a big explosion or kind of thing, the sun's going to die. And then, 8 minutes later, it'll be total darkness.
Yes, like if it goes away, we're just gonna be like.
We better hope that at that point in time, we can create nuclear reactions. Because that's where our energy will come from. If we could harness nuclear power with fusion and fission, we would not need the sun. That's literally how much energy we'd be gaining. If you could use hydrogen to create nuclear fusion, you could actually use that to create your own light source of cells. I mean, people already do this. You know there's indoor like farms that exist. It's like terraforming or something, where you use different levels and the water from the top level goes down to the next one, but it's all indoor using certain types of light. Miss Myers does it if you look down the hallway right now. Actually, you can probably see the lights on, right? Are they on? Are they not on yet? They're like always on. Anyway, using certain types of light that allow plants to absorb the energy from that light. And using
It's too bad to just go by plan.
yeah, but when the sun burns out one day,
But before it burns out, it's going to get so big before it explodes.
it's right. So the solar system anyway.
Yeah.
See this, is it? Is
But
that
it's
clear?
like it gets big,
And then,
and then
yeah,
it's
supernova. Yeah, that's right. Supernova.
If the sun goes away, doesn't that mean like everywhere's gonna be like super cold?
Yeah.
Yes, again, we're only in one location. We're in the solar system that we know, which is inside of the Milky Way galaxy. Milky Way galaxy is a tiny, tiny fraction of the universe. So our sun only gives the 9 planets energy in the line. Once it gets far enough away, it's not even giving energy off anyway.
Oh, right.
So it's pretty much going to create coldness on the Earth.
Yeah.
And on like Venus and Mars.
Will we be able to reach
But-
absolute zero?
one
No, because
explosion.
we have mass and mass.
Explosion magnetic field in case universe.
Say again?
Magnetic field, when the explosion messed it up.
Mars is 5.
There'd be a lot of problems. But listen, we should look at the video of what happened with sun. We're about done. Unless you found the one you sent me, you want to go? Do you have it? Can you AirPlay? Let me get off AirPlay. Hold on.